In this video, we're going to look at the bending moments example 3. This occurs on page 11 of the course notes. So this is the problem with which we're presented. We have our beam with some point loads applied. We also have a uniformly distributed load. And if we notice at the left-hand side, there's a moment being applied at point A, and that's relevant. As we'll note from some of our other examples, we often look for a bending moment at point A, and with our convention of looking to the left, conclude it to zero because there's no forces acting to the left of A. But with a moment being applied in a counterclockwise direction at point A, we can start off with the bending moment at A by stating that the bending moment at A is equal to negative 18 kilonewton meters. Remember, that negative comes from the fact that the arrow is pointing in a counterclockwise direction. Moving from left to right as we do, we look at our next point indicated on the diagram, that's point C. So we'll mark a cross section through our diagram with the red dotted line. This helps keep us right so we know what we're looking at. Now, for the bending moment at C, we can start off by adding some things we know straight away. We have that negative 18 to consider that's been applied at point A. And then we have a 9 kilonewton force acting upwards, but importantly in a clockwise direction as a moment relative to point C. So as it's clockwise, we'll add 9 multiplied by the distance from C, between A and C there's 1 metre, and we've considered that force. Now we need to take into account the UDL and how it applies between A and C. Now we know a UDL's effective point is going to be in the middle, so we'll have a force being applied here, and that's going to be at a distance of 0.5 metres from C. The way we calculate a UDL force is we take the force per unit length, so in this case 2 kilonewtons per metre. We're subtracting, because this is acting in a counterclockwise turning motion. We multiply by the entire length, that's the 1 metre between A and C, because that's how much force is being applied. And then lastly, as we always do with moments, we multiply by the distance it's effectively being applied at. So that's 0.5, that's the distance from the midpoint of AC to C. So we multiply by 0.5 there. And if we sum all of this up, we have minus 18 plus 9, and minus 2 times 1 times a half is minus 1. So we're going to be left with a total of minus 10 kilonewton meters. We found our bending moment at point C. So I'll erase the wee notes we made on the diagram here, and then we can look again to find the bending moment at point D. I'll mark our line passing through D here, thereabouts. And so MD, let's consider what's going on here. So again, we consider the negative moment at point A. The force being applied at A, 9 kilonewtons at a distance of 2 metres from D. And now we consider again the UDL. Now this time the UDL is effectively being applied at the halfway point between A and D, which is a distance, it's already indicated in the diagram, but I'll write it here, of 1 metre. And the force that's being applied, well, again, we've got 2 kilonewtons per metre times 2 metres of distance in total is 4 kilonewtons. So in our diagram here, we're subtracting, remember, and it's 2 kilonewtons per metre times 2 metres times the point it's applied at, which is 1 metre. So if we look at our numbers again, add them all up, we've got minus 18, this time it's going to be plus 18. That's going to cancel out, and that's going to leave us as minus 2 times 2 times 1, which is minus 4 kilonewton meters. And lastly, we have our moment at point B to consider. Now, as we've come to expect in these problems, when there's no moment being applied at B, we might be expecting is going to be 0 here, and it turns out it is going to be 0. But let's do the calculations to convince ourselves that this is indeed the case. So as with the previous problems, we have our minus 18 moment being applied. We add on 9 from the force being applied at A, multiplied by a distance of 3. Then we consider the effect of the UDL at point B. So this is applied in the middle of the beam. So this is a distance of 1.5 meters from B. And the force being applied is 2 for the 2 kilonewtons per meter, multiplied by 3, which is the distance between A and B. So that's a 6 kilonewton force. So in our equation, we're subtracting that 2 times 3 for the load being applied, multiplied by 1.5 for the distance at which it's being applied relative to point B, in that midpoint between A and B. And if we add all these up, as we suspected would be the case, the bending moment is 0 kilonewton meters. And that concludes example 3.